right, hello everybody. Welcome back. I hope you enjoy the music that was put together by our main organizer, Lindsay Deeds. So I feel very honored to introduce you to our next speaker, who is Dr. Eric Lin. Dr. Eric Lin manages a small team of data scientists at Metro Transit whose mission is to make data available and useful for the decision-making throughout the agency. Recent projects have included spatial and temporal bus ridership modeling, bus speed and delay analyses, and travel behavior studies. The team relies heavily on R for data handling, visualizations, and statistics, and R-Shiny for creating tools specific to business needs. Prior to his career in transit, Eric was a quantitative ecologist studying interactions between insects and plants. And one other notable accomplishment that Eric didn't list in his bio was that he had successfully converted me from a frequentist to a Bayesian when I worked with him at Metro Transit a few years ago. So without further ado, Eric, the floor is yours.
Thanks, Kim. And I am so glad to hear about that accomplishment. I don't think I fully had appreciated that, but yeah, I'll take that win. I really want to thank Lindsay and other organizers for inviting me to be a part of this. It's been really fun so far. I'm sad we can't do it in person, but this feels like the next best thing. So it's really nice to be here. And what I'm going to do today is walk through a real applied use of statistics in data science in terms of an active question that we're working on at Metro Transit, or a set of questions, as an example of how we're trying to kind of bring probabilistic understanding to people inside a context where they don't usually think that way. And so it's an example of how we're using these tools. I'm going to go through these slides and then we'll switch over to a markdown document where we can get into some more of the code. But I do want to give you this background first. Okay, so just setting context, I'm hopeful that most of you are familiar with Metro Transit in being the largest public transit provider in the Twin Cities region. We cover 7 counties, 90 cities. We have a lot of bus routes. These are just some high-level statistics, and the bottom line is about 250,000. Oh God! Oh no! What is happening? Oh dear. Okay, so all of the things I'm about to tell you are very pre-COVID. Okay, so I just want to get that caveat out of the way that we're struggling right now with responding to this worldwide pandemic. People's travel behavior has changed a lot. People's needs, essentially, for getting around have changed a lot. So basically, what I'm about to share with you, I just want you to know is kind of already out of date. It's not in terms of our fundamental understanding, but it is in terms of like what we're doing. The other piece of context I have to share with you is, of course, we are really embedded in a lot of the communities that have been impacted by George Floyd's death, what followed in terms of unrest and sort of the rebuilding that's ahead of us. I put this slide in here. I really like it because it has this, the iconic selfie that George Floyd took, kind of the centerpiece, but it's also, this sprung up in the 2 days or so after his murder. And it was, really, to me, touching to see this memorial be built around our bus stop on our single busiest bus route, which is the 5. So I only add this because it's a context that's really front of mind right now in Metro Transit, and we're trying to understand like how we should respond and also how we've served these communities in the past and should going forward. So all to say, so we have COVID, we have George Floyd, and then the main part of what I'm going to be talking about today is the sort of before all that context. And what you're looking at here is a figure showing our daily bus ridership from 2015 through the end of 2019. So each of those gray dots is a value of the number of boardings that took place on our bus system. And you can see a bunch of fun patterns. Hopefully you can see my mouse here, but those of you that have lived in the Twin Cities for a while will note these big spikes that seem to happen about every end of August, beginning of September. You're nodding because that's the state fair, right? And so likewise, you get these big drops around the turn of the year with holiday time and so forth. But obviously the big pattern that we Metro Transit found worth exploring and very concerning is the pretty linear decline that happened over the past 5 years in terms of bus ridership. This is a national thing that's been going on. It's it has a lot of different causes, right? Very multivariate problem, from auto availability to where people are living and so on and so on. Not to mention our own service. But we wanted to understand a little bit more deeply, like what is both behind this pattern and also what can we do about it from Metro Transit's perspective in terms of improving our service to keep rides. So this overall decline is actually made up of lots of different routes. As I mentioned right before that big COVID splash, we have about 120, 125 different bus routes. So what I'm doing here is showing the same data, so taking from 2015, the annual ridership, and 2019, the annual ridership, and just visualizing it as a percent change. So each of those bars is a bus route. They're colored by the type of service, a route class, a route type, which I'll come back to through the talk here. But basically what you can see is most routes are declining pretty substantially, about 20%. There are a handful, but definitely the minority of routes that have been increasing over that time. And so, the applied question here is, what can we understand about what routes are succeeding or not in terms of their ridership? And how can we then make changes to our service to get them more into the positive line? Okay, so when we went to look at these, the simplest thing we can do before we get to where these routes go, who's on board, what specialty purposes the trips are serving, we really just wanted to get a high level understanding of kind of what the dynamics were. So we're going to look at the route class or route type, and there are a few different ones, and you can probably imagine they reflect the different user markets, right? So there's a core local service, which runs all day pretty frequently, suburban local service, which is less frequent, but kind of tries to serve people who don't have or want a car to get around more less dense areas. We have supporting local service, which is kind of that like feeder service to a light rail, and then commuter and express service, which is really peak time and direction type service from like a park and ride in the suburbs to downtown St. Paul or Minneapolis. So going back to this, going back to this figure, I mean, one of the things you'd want to know as you thought about how did routes change over time is, what is the amount of trips that those routes are making? Because really, when you look at transit ridership, you're talking about kind of a sampling process. You're putting a bus out there for a certain number of times or a certain number of trips. The more trips you make, the more riders you'll get, right? So you won't necessarily get more riders per trip, but you'll definitely get more riders the more trips you put out there. So one of the things to take into account as a predictor is how much each individual route is being run. So when I looked at this, the average route didn't change really, and you can see that histogram on the right there, but about 30% seems like a good cutoff for saying that a route has changed significantly, manageable number in terms of numbers that have increased or decreased service. Okay, so the goal in this analysis, we want to capture, first of all, the network-wide ridership change. So that big orange line that you saw going down, that's a system dynamic, right? Most of the routes are sharing that trend. Something is happening with people's travel behavior that's impacting lots of different routes simultaneously. But we also want to understand how the routes are different by their type. So, is the commuter express market changing the same way that the local is? And then finally, we have to account for this amount of service we've been doing. So this is kind of what I would present to our service planners or analysts to understand. What am I going to try to tell them? And our job then in our data science group is to translate this into a statistical evaluation, right? So translating that into, we have like a linear predictor in terms of the amount of service that's being put out there. And then we have a couple different groupings. So we have a hierarchical grouping of route class. So we have a certain number of routes that are in the commuter express, a certain number that are in the core local. And we think that they share some characteristics. So we're thinking about them as being grouped. And statistically, we're thinking about their variance being grouped or pooled. But there's also this overall thing that's happening. So we know that these routes don't exist on their own. They're inside this network. And so there are lots of different approaches to making this work. Essentially what you're talking about is, nested modeling or, strong covariance within groups. You can think about mixed effects modeling if you're familiar with that. And I'll get to in a second what we chose to do. So first, just to get specific about how we're quantifying the change here, because the ridership is so different across some of these routes. Some of these routes serve 10 to 15,000 people a day, some of them a few hundred. So to scale those together, we're going to do essentially like a log response ratio, taking the 2019 over the 2015 and taking the natural log of that. That, as you can see on the right, just has a really nice normal distribution once you've logged it, and it has good properties for modeling. So it also has an interpretation in terms of that rate of change. So we're taking a shortcut to doing like a time series analysis between 2015 and 2019 by taking that log response ratio, but we can still say, once we back transform that with an exponential, using this example here, you can see that based on that y of minus 0.29, we're talking about 75% of the ridership remains in 2019 that we started with in 2015. So that's our response variable. That's what we're going to try to predict in this statistical problem. So shout out to the good Reverend to bring us back to probability. And this is obviously not something that I can really walk through that often with the transit planners or the analysts or the people that are trying to get the buses in and out of the garages. But for me, it's important because I have to remind myself that we're talking about events that are being drawn from possible outcomes, right? And that's the whole basis of our probabilistic understanding. Lots of things could happen. Which of those things happen is kind of the interesting part. And if we can make a model to explain those, that's what we're trying to do. So if you've taken this, and I know we've got experts in Bayesian, Dr. Knudsen, and probably other people that know a lot more about this than I do, but the way I really like to think about it is understanding it based on a model and data. So what the left-hand side there is saying is the probability of the model you're interested in, given the data that you have, is proportional to the probability of the data given the model, which is a likelihood, times the probability of the model without any data. Well, the probability of a model without any data doesn't really make sense, and this is a problem that a lot of people have with Bayesian inference, I guess, but what that is the prior probability. So not knowing anything about your system, but you have an idea of a model, that's your prior expectation, okay? So those two things are combined, and we kind of allied the part about understanding the probability of the data by comparing rather than trying to quantify this. So when we translate this into a modeling framework, and this again is something that really works for me personally, is to think about them as being draws from distributions. So that tilde then is you think about a draw from a distribution, and it can be a single event or it can be a vector. So ultimately, as I showed before, we have a nice normal distribution of those ridership changes. So that's a mean and a variance. The way we build the model is we take that mean and variance and decompose it a little bit and nest it a little bit, okay? So we've got a linear predictor. I think I might have annotated this. Okay, so we're drawing the route change from the distribution of the probable changes. And that expectation is determined by the class of the route and the impact of the change in hours. Now what I've done is nested these two things so that the impact of the change in hours depends on the class. So the slope of that response depends on what route class you're in. And then the intercept, which is sort of the baseline expectation, not knowing anything about how the service changed, is also nested inside its class. And the way you do that in the hierarchical sense is you're basically drawing those coefficients from parent distributions. So the slope here in that's modifying the service change is actually drawn from a potential distribution of those slopes. Okay, so it's kind of draws all the way out. Okay, some actual R syntax. I am, and we'll go back to the R Markdown in a few minutes, but I am a really big fan of a package called Rethinking, which is meant to go along with a book by Richard McElreath called Statistical Rethinking. And the reason I like it so much is that the syntax matches what I've diagrammed here in terms of those distributional modeling equations. So you literally can put in the same equation with a little bit of translation. And what you're doing is seeing how that model can be put into, in this case, a STAN, which is the Bayesian inference platform that I'm using. It can be translated into that framework for you in R. And so like with the, people love to mention the tidyverse and tidy models we heard earlier this morning. It just fits with the way I think. I really get it. Like, it makes sense to me. This is one where this just like really makes sense to me as somebody who's coming from this probabilistic drawing understanding, because I can map those models right into this framework here. So what rethinking does, you can use it in different ways, but in this way, it translates this into a STAN model with the STAN syntax, which is totally outside of R and a little bit quirky depending on how you think. But so when I run it, this is the sort of output we can get. So here is, for instance, the intercept. So as you remember with Bayesian, you have a distribution of outcomes. So you have a posterior probability, and that's what I'm graphing here. So these are slides that I shared with our planners, and this is one of the things I want to emphasize with the Bayesian approach is it's super intuitive when people see the outcomes, because it's how they think, right? So they don't want to know the probability of the data given the model. They want to know, like, what's the probability of these answers here? So this gives us a way of translating that that uncertainty in our understanding, or capturing the variance in the system. And so you can see right away, okay, if I didn't know anything else, I'd say most of the core locals have been doing kind of the worst out of our system. The Commuter Express seemed to have declined less from 2015, okay? And again, this is showing, and there's a little rug plot underneath there that shows you the actual observed, but this is one nice thing about the Bayesian framework, again, is this is taking the model output if service had not changed. So this is just the intercept values. And then this is more of a fun one because we can combine all the different posterior slopes that come out from the modification of the change in service hours. So the more service, the more riders. And if you scale it as a percent, as I've done in this plot, you can kind of really make a few concrete conclusions, okay? So the vertical dashed line, this is essentially the intercept, right? So 0 change in hours, that means the slope is multiplied by 0. So you can see that this value on the y-axis will match the previous slide, right? So the core local is down close to 25%. But the other fun thing is you can look at the horizontal dashed line, and this is where service planners were interested, because this is where I could tell them, look, this is such a strong pattern. If you wanted to maintain ridership at the same level in 2019 as it was in 2015, you would have had to have 25% more service out there for that year in the core local. You would have had to have close to a third more service out there in the Commuter Express. And those are buses and drivers and planning that we don't have, right? So those are really big numbers, and that like kind of counterintuitively helped them understand the scale of the problem, to say, yeah, we would have had to put 125% of service that we were running, which we already thought was a lot, just to maintain. Okay. Then the last thing we can do, which is very useful, is some scenario planning. So once we have these Bayesian models fit to take new draws from those probability distributions, with a different input is very straightforward. So in this case, we said, okay, what about if we had run a little bit more service on this one particular route, what would the outcome have been? And so, it can provide, obviously we've got the observed values, the modeling output. So the predicted range from the model was very good. It captured, exactly what the actual ridership was. And as we modify the number of hours that are out there, we can see what the predicted change would have been. So we would have been something north of 375,000 annual rides instead of 350. And of course, we can do that in a distributional way as well. And again, with the posterior probability distribution, I don't call it that when I'm talking to the planners, but they get it. They know that there's uncertainty in the outcome. Like they might implement these 7 more hours per week, and they might only end up with 10,000 annual rides more, or it might be 40. And those are kind of reasonable bounds, but the uncertainty is part of the planning process. Like they have to decide whether that seems like worth it to invest in those hours. So those are a few ways that we try to use the output of those. So before I switch over to looking through the code in a little bit more detail, some summary, I think it's important for us to bring uncertainty into planning and data science. And I know that you all know that, but I'm just reflecting that it's something that most people don't think about when they're trying to make decisions inside a business or an agency. And so having these kind of integrated probabilities really helps communicate that, I have found. So also the nesting and hierarchy that we're able to do in the Bayesian framework is really nice. I also, most problems in transit are multiple hierarchies in time and space, and so this is just something that we need to do. The last bullet, I'll just say, this also makes you be really explicit about what you know in terms of your domain knowledge, as well as your stats knowledge. Honestly, like the stats part is typically easier than the domain part, as probably some of you have encountered, as we try to translate a problem into a probabilistic draw. You start to have to think hard about what it is you're actually measuring and what you want to know. So I actually find that to be a benefit of doing things this way, because that's a way you can kind of build with someone who's not a statistician to kind of increase the chance of getting the model right. Okay, so let's stop sharing and switch over to the Markdown document. So this is available in the GitHub for the conference. And now that you've sort of seen what I was doing, you can go through and look at a few things. I'll point out, I won't belabor this, but I'll point out a few things. The first is that we are data table shop in Metro Transit, basically because of the experience of me and a couple other people that just brought that in from the outside, and Kim will be talking about that later. I'm super excited about that. I guess it's tomorrow. But so we do a lot less tidyverse and a lot more data table syntax. And one of the reasons for that is because we're dealing with data sets like bus locations that are 1.5 million rows per day that we're trying to aggregate and summarize, and it ends up being a lot significantly faster to do that in data table. So that carries over. The data are actually available in that GitHub as well. So if you wanted to play around with the routes and kind of see the scales and the changes that were going on in terms of that, these are public data, so you can have at it. I mean, one of the things that you might want to do is, one would do is look at, what are the communities these routes are serving and what might be changing differently in one versus the other. So I'm going to skip through, the visualizations that you just saw. I've included those codes. Okay, so I just wanted to get to rethinking. So as I mentioned, rethinking comes from this very nice book, which is very readable, and it really is like a perpendicular way of approaching Bayesian thinking in my experience. So if you're interested in kind of taking a second look at Bayesian analysis, or you've been frustrated in the past, I think that might be a recommendation. And then rethinking, as I mentioned, translates things into Stan. So there's a package called rstan, which is a wrapper for Stan, which is its own platform and language. And this is another one of these that can be sort of hairy to get installed. So thankfully, we're not trying to do that in person today. So this, I'm going to show you two models that I built. The first one is just a null model. So basically what I did was take that distribution of changes and draw it from a normal distribution, but not give any predictive information in there. So I just did essentially a null prior of a normal distribution very narrowly around 0. And basically that's just going to describe the distribution for you, right? So the way this is done, you specify your model and then you run it using the rethinking. You get lots and lots of output if you use this debug equals t. So you can see what's going on. It eventually, this part right here is the Stan syntax. So if you were going to submit a model to Stan, it actually provides that to you. You can do that directly. Then there's lots and lots of fun errors that only seem to pop up when you're doing this, when you're rendering an R Markdown document. We're going to ignore that. You get a nice click through as this is running in terms of how the iterations and the samplers are going. Again, these are chain samplers, so these are running. And then, of course, you get little output. So here we're just describing sort of the shape of the distribution, right? There's a mean and a variance. And those means and variances have their own means and variances. And you can see some typical Bayesian valuation statistics for the model, like the effective sample size and a version of the R hat. So then, as I mentioned before, we ended up with this kind of nested model of the slopes and intercept nested in the parent distributions. I'm not going to go through the fun part, which is building models 1, 2, and 3, which almost but didn't quite work. But this is the one that we came out with. So as I mentioned, you can kind of basically pull out the parent distribution and then all the sub distributions. And what I encourage you to play around with is how you then get back to these kind of output figures where you're translating those matrix models back into distributions that are fun to talk about and share. So I'm going to stop right there in case there are any questions, but thank you for your attention.
Thank you, Eric. This has been very informative. Yeah, we do have one question from Christina Knudsen. So she wonders what combined bus rise and light rail rise looks like. So she used to take a bus that got replaced by the Green Line.
Absolutely. That's a great question. So I'm going to go all the way back to the very beginning. If you look at this trend on the light rail system, it's actually positive, but not enough to account for this decline. So right now, sorry, pre-COVID, let's say not right now, but February 2020, light rail ridership was about 1/3 of our daily ridership, and the bus was about 2/3. But that share has been changing over time, but the decline in bus ridership is not fully accounted for by people like yourself switching over to light rail. So still something we're seeing.
All right, and we got another question from Jay Smith. So as a resident of Minneapolis who lives between the 5 and 14 routes, what do you see as some of the primary driving factors in reduction in the local service ridership?
That's a great question. So those routes are both going to be over here.
Eric, sorry, I think your Lisa pointed out that you're probably sharing the wrong screen because we're still seeing the R Markdown.
Funny. Yes, I was. Okay, well then I'll just stop and answer the question. So thank you for that. So one of the features we've seen is that the core local routes were the ones that were declining a lot. Okay, so they were the busiest, but they also were losing the most ridership. The Transit Center, which is sort of a nonprofit analysis group out of New York, their phrase is the car is the competition. I think that captures pretty well what's been going on with local bus ridership, especially before 2020. The economy was going pretty well, and people were able to afford cars that couldn't before. There's a lot of other options, you know, everything from scooters to Uber, whatever you think about. All of these contribute to people using transit a little bit less, and that kind of compounds into the losses that we saw. So, you know, our focus with Route 5 and Route 21, which is the one that goes on the Lake Street line, now is to improve those routes, and especially since George Floyd, we need to upgrade those routes, provide better, more frequent, faster, nicer service, so that people will come back and continue to use us as kind of a fundamental part of those communities. So that's our goal right now, and we're working hard to do that.
Thank you. And then, so we run out of time, but we do have one more question, so probably you can answer this briefly. So Charles Chen asked, how do you compare WinBugs and rethinking?
Yeah, so WinBugs is a Gibbs sampler. That's the GS in bugs. And STAN, which underlies rethinking, is what they call Hamiltonian no U-turn sampling, not related to the hit musical, but it is, so it's a different approach to finding the right answers inside the sampling. And if I'm going to explain any more of it, I will be in trouble. So I hope we're out of time.
Okay. Thank you so much, Eric. This has been great, and yeah, and for all our attendees, we will be back in 4 minutes at 11:50 for our next speaker. Thank you.
Thanks.